Right, so from the wee workbook that was made up for the maths camp, question 1.22. Just to recap on that, a proof by induction. Reading it out, it simply says, prove by induction that for all natural numbers n greater than or equal to 1, 3n to the 5 plus 7n is a multiple of 5. It's required to prove 3n to the 5 plus 7n is a multiple of 5. In other words, divides by 5. Well, it's a proof by induction, not a direct proof. So what we need to do in this case then is show that it's at least true at the start. So it's showing that it's true, it was for n greater than or equal to 1 in natural numbers. Check for n equals 1. Well, at n equals 1, that would be 3 times 1 to the 5 plus 7 times 1. Well, that's 3 plus 7, which is 10. 10 divides by 5. 10 divides by 5, which means it's true for n equals 1. That's the first part. Now, assume it's also true at any arbitrary point along it. Assume it's true for some other n further on, for n equals k. I'm not saying it is necessarily true. Assuming it's true at n equals k, that would mean that if I put k instead of the n, then 3k to the 5 plus 7k should also divide by 5, which means it should equal some multiple of 5. So 5 times m, for instance, where m is some natural number. And then consider after that, consider n equals k plus 1. In other words, if it was true at some point, at k, does that mean that if I go to the next one, I get the same result, that it's also true there? If it does, I've proved a connection. I've proved that if it's true at a certain point, it'll certainly be true for the following one. And then since I know it's true at the very beginning, I know it's true for 1, that means it must be true for 2 from the connection established, which means it must be true for 3, and so on. So considering n equals k plus 1, well, that means this original expression would be 3 times, if n is k plus 1, k plus 1 to the 5 plus 7 times k plus 1. Well, nothing for it, just multiply this out. I'm quite happy with this little thing here, because I recognise that as a simple little binomial. You could batter down Pascal's triangle if you like, but you probably can remember it, the 1, 5, 10, 10. So that would be k to the 5, 5k to the 4, 10k to the 3, 10k to the 2, 5k plus 1, and then plus the 7k plus the 7. Very nice for most of it. I want to show it's divisible by 5, and it's full of these factors of 5s. Don't like this wee character, or this little one here, or this little one here. But if we take those bits out, I've got a 3k to the 5, and you think, no, 3k to the 5, there it was there. And the rest are all fine. I could gather them, call them something else, but I'll just write them down. So that'll be 15k to the 4, 30k cubed, whoops, well, it was a bit worse, 30k squared, 15k plus 3, not so nice, plus 7k plus 7, well, that's much better. And then you look at these parts here, the parts I don't like, well, those two are quite nice, they add up to a nice 10. So if I take out that first bit, I've got 3k to the 5 plus 7k. As the little ones that are spoiling it so far, but everything else is fine. I've got 15k to the 4, a 30, which is a multiple of 5, a 30, which is a multiple of 5, a 15, which is a multiple of 5, and a 10. So it's only this one here. But calling in the inductive hypothesis here, that initial statement, that initial assumption, assuming that it was true there, if I call that into play here with this part, then I can replace that using this. But I'll need to jump up to the top here. So up to the top, I'll try and not take away my little trump card just now. That means I've got, instead of 3k to the 5 plus 7k, I can call in number 1 and call that 5m, because it was equal to that. plus, and then yes, it's a little bit tedious writing all these down again. Maybe I could have thought of some little device, I could have put down some simple term, I could have replaced them all by, but it keeps them all nice and happy. They're all together playing just now. And then everything's got a multiple of 5, take that 5 out, I've got an m and a 3k to the 4, and a 6k cubed, and a 6k squared, and a 3k and a 2. Thank you very much. You can go home now. Which means I've got a multiple of 5, which means is divisible by 5. Since the m's and the k's that I've got in there were all natural numbers, which meant I've proved that link now. Which meant if it were true for n equals k, it follows that it's true for n equals k plus 1. And since it was true at the very start, well, let's say it was, that's a wee bit too fancy. Since it's true, oh that's just as bad, for n equals 1, that means it must be true for all n, for all the natural numbers, n greater than or equal to 1. The initial statement, which was required to be proved. Right, I'll stop that one there, because if you make too many mistakes, I'd have to start the whole thing again, and there was enough little hesitations in that one. So in the next part, I'll move on to questions 23 and 24, the two proof by inductions that had the matrices in it.